Hey guys, welcome back. Mr. Smith here. If you enjoyed our last discussion where E equals mc squared explained how matter gets destroyed every time energy is created, you'll really like this one because this is even more mind-blowing. What we're going to start with is to talk about radioactive decay, talk through the common kinds of radioactive decay, and talk about how and why they happen. And it seems innocent enough, right? We start in 1899, in fact, with Rutherford identifying alpha and beta particles. So we'll talk about why those happen. 1900, Paul Villard in France discovers the gamma ray and figures out what that is, just high energy light. Here's the thing. If you tried to make blueberry muffins and all you had was blueberries, you wouldn't really have good muffins. And so it probably stands to reason, if you're thinking about it, that the discovery of the nuclear atom and the fact that all the positive charges were crammed into the tiny space of the nucleus presented an obvious intellectual difficulty. They hate each other. How could you possibly get this stuff to stick? And so, not surprisingly, if you thought that neutrons might actually have a role in helping to get those guys to get along a little better by separating them, I don't know, kind of like playground monitors in a school for little hellions, that was the right idea. And so what you get is, if you look at our chart in the textbook of stable nuclei follow basically this trajectory. And what you get in this solid line is a line of the number of protons equals the number of neutrons. And you see that that's not really a successful model for how you build an atom once you get past a certain size of atom. So the more protons you pack in, turns out you need a little more neutrons to keep those protons from fighting each other and falling apart. So what we're going to do in this deck is to talk about these 5 main modes of decay. Before we get there, let's dig a little bit further into how the nucleus really works. Here you've got an image that represents 2 different strands of ideas coming together. So here's a formula down here for the electrostatic force. This is the Coulomb force. These are protons pushing against each other inside the super small nucleus. It's a very strong force, and the protons hate each other. So here's the story. In 1935, Hideki Yokawa, a Japanese physicist, suggested the existence of a strong force, his words, strong nuclear force, strong enough to combat that force. And here's the notion. Protons and protons can exchange the strong force with each other, and protons and neutrons can exchange the force with each other. In Yukawa's formula, you see basically what looks like the formula above. It gets weaker as the distance gets bigger, but there's an extra exponential component here. So what it turns out to be is that the strong nuclear force is very, very strong, stronger even than the electrostatic force, except it drops off pretty quickly because of this extra term here that makes the force become small over distance. So this is what you see, that in small nuclei, the strong nuclear force really dominates and you get stable nuclei. In bigger nuclei, the strong force starts to wear out maybe, and it's not able to constrain all those nuclei, all those subatomic particles together. Okay? Here is a really cool chart. It's a variation of what we have in our textbook, and it's got a little more information in it. So here's our line out here of neutrons equals protons. What I wanted to show you is the 4 main things that you're going to see here as we discuss it. First of all, you get atoms that are just huge. They're absolutely enormous. A few of them in the green, they actually just fall apart. So we're thinking of things like uranium-235. That is the very first element that was used in an atomic bomb. It literally falls apart into fragments of other atoms, barium and other stuff that we'll talk about. Well, what's less catastrophic than that? Well, alpha emission, all these yellow ones, what happens when you have alpha emission is an alpha particle, which turns out to be a helium nucleus, goes spitting out, and you're left with a smaller nucleus that has less protons and less neutrons. This is basically like the I don't care what you guys do, just go outside. Now, a little more sophisticated than that is beta emission. So we'll talk about how beta emission works. Beta emission occurs when a neutron falls apart into pieces. beta plus emission, almost the same kind of thing. We'll talk about that. That's pretty mind-blowing. And that's a good way to start. So those are 1, 2, 3, 4 main things that we wanted to talk about at the very beginning of the deck. And we'll show you how they then work. So here's how alpha decay works. Very straightforward. Ernest Rutherford realized what an alpha particle is 2 protons and 2 neutrons. Same thing as a helium nucleus. So we've got a mass of 4 and 2 protons. You can check the math and you can see how it works. Our samples that we use in the lab, like all the samples that schools use for alpha sources, contains polonium-210, and just follow the math. See if I have polonium-210 with 84 protons, spits out an alpha particle. What's left in the disk is this non-radioactive 82 version of lead, or the 206 version of lead. So a sample example, how does radium-226 decay? Well, first thing I have to do is if I see radium, I need to go to the periodic table and look up the fact that radium contains 88 protons. So once I've got that, then I just write down the 226. And as I did above, I'll write down my 2 alpha 4 and just do the simple math. I think it's easier to do the numbers first and then worry about the other thing later. So I've got 86 protons and an atomic mass of 222, and that turns out to be radon. Let's talk about that in class. That's why you do home inspections in New England. All right, next one. This is so simple. I don't even do an example for it. This is our gamma source. It's cobalt-60. What happens in cobalt-60 decay is this. You have an excited nucleus. So just like an atom, a nucleus can have energy levels and it can bounce and slosh around. And if it has too much of that, it may choose to spit out some energy in the form of a gamma ray. It's just high energy X-rays, basically, and they're not even a particle. So it doesn't change the atom at all. All you do is, in writing it, you just get rid of the asterisk. It's a freebie almost if you get this on a test. So just say thanks. So buckle up, because now we're about to go to crazy town. What you're looking at is a picture of a cloud chamber. It's full of water vapor, and what happens is if charged particles cruise through it, they leave a track, kind of like an airplane leaving a contrail in the upper atmosphere. So what's crazy about that? Well, the title of the slide says matter and antimatter. Okay, so those are real things. Matter is matter of like protons and electrons, and antimatter is things like antiprotons and antielectrons. Well, what in the world does that mean? Here's the deal. E equals mc squared has 2 sides, a creative side and a destructive side. If energy and mass are really different forms of the same thing, then in our cloud chamber, what we might actually see is an image of nothing coming in. Well, it's not nothing. It's a gamma ray. And decomposing, falling apart when it collides with an electron. So the gamma ray loses energy to the electron, then falls apart. And from the energy of the gamma ray, we get 2 particles that are created from not thin air, from thin energy. This is a very real thing, and it happens. You can even go back and check it out. So reverse the slide, pause the deck, go back and check out my first example. This was really colorful. You'll actually see examples of this very thing happening. So energy giving birth to matter. Crazy. So it goes the other way too, right? So, okay, here's an example. What we've got here is a piece of antimatter in one of our nuclear reactions cruising out and just bouncing its way through the real world. That thing is an antimatter electron. What is that? It's an electron with the same mass as an electron with a positive charge. It's a real thing. So this positive matter electron, called a positron, finds an electron that's just lurking around minding its own business, and they annihilate each other, is the process called. That sounds pretty final, huh? Yeah, the particles just go away. Bap! Never existed. And what happens is you get these 2 photons with very specific energies that come spitting out. But anyway, that's called matter-antimatter annihilation, where matter goes away and gives birth to energy. Okay, that's awesome. So now we're here at the neutron, which is the heart of all of these electron decay styles. What I've got inside of a neutron, believe it or not, is 2 things that you might have thought of on your own: an electron and a proton. That's right. You just add them together and you get a neutron. Not quite. This is fine, right? Now it makes sense if we just invent a new particle and throw it in. The fact is that this was discovered. The antineutrino is an antimatter neutrino. It's a key part of building a neutron. It was discovered by Enrico Fermi, a famous Italian physicist. But the way the neutron decay works is like so. You see it in the image here, and I'll just write it down for you, and then we'll apply it to a real atom. So we've got a neutron. When it cracks open and falls apart, it gives you a proton that you get to keep. Congratulations. And then what happens is a negatively charged particle, a beta particle, an electron, comes flying out of the nucleus. And then because we need it for conservation of other physics ideas, this antineutrino comes along for the ride. Now, what's up with the neutrino? It's got no protons and no mass, and I write a hat over it to indicate that it's antimatter. Okay, you good? All right, so here's carbon-14. So carbon-14 is the radioactive version of carbon that's out there that lets us understand how old things are, and it does decay by beta emission. So what happens? I think it's easier to focus on first the mass. The mass won't change because the beta particle won't carry away any mass with it. What happens? The neutron on the inside of this gets cracked open and the proton is kept. So the atomic number goes up by 1. That's the next step. All I do now is go to the periodic table and look up what element has 7 protons, and that turns out to be nitrogen. The rest of the equation you just copy down verbatim. So -1, beta, 0, plus an antineutrino, and there I am already getting tired of writing the zeros on the neutrino. You can drop them too if you want to. So positron decay is the exact opposite of the thing we just did, but for some reason it still freaks me out a little bit more. What happens here? An atom that's down in this region here, the orange, decides it wants to migrate a little higher and become a little more stable. How does it do it? Well, out of energy, what it does is the atom manufactures all the parts that it needs to convert a proton into a neutron. So it manufactures a positron and an electron, keeps the electron, it manufactures a neutrino and an antineutrino, and it keeps the antineutrino, and it builds out of those things a neutron. And so what you get is this stuff out here is what comes flying out of the nucleus as junk. Okay? So in the case of oxygen 15, you're just going to write your 8O15, and just imagine what would happen if we took a proton and converted it to a neutron. The atomic number goes down by 1, and the mass doesn't change. So I'm going looking for element number 7. Oh yeah, we talked about that guy a second ago. Becomes nitrogen. Then what's left over? Again, you just copy this stuff verbatim. The thing I want you to notice though is this is a +1. That's a dead telltale giveaway that this is positron decay. So you want to make sure you're aware of that. And then you notice I write my neutrino without the hat on it. Okay, so that's positron decay. One last one and we're good. In the case of electron capture, just like positron decay, we have an atom down here that's below the island of stability and he wants to hop up. What happens is an electron that ventures too close to the nucleus gets captured, and the proton then, or the atom, manufactures the neutrino stuff that it needs to convert that proton into a neutron. So it's a very similar process. As far as school stuff goes, this is one of the easy ones to look for too. Rubidium-83 is one of the isotopes that does it. So I just have to go and look up that rubidium has 37 protons and 83 is the mass. And what makes it a telltale giveaway, they're going to write it like this. You're going to see a -1, 0 on the left-hand side of the equation. Electron capture is the only time you see that. And what happens is, just like positron decay, proton number goes down by 1. We get element number 36. Mass doesn't change. And then we spit out the neutrino part of the pair of neutrinos and antineutrinos that we didn't want. Finally, element number 36 is krypton. Okay? So that's a bundle of stuff. That's how radioactive decay works, how E = mc² gives and takes away. You might have some questions. We're going to work with this next time I see you. So bring your questions to class. Take care and have a great day. Bye-bye.